Today, we're going to look at the correction of interferences in EPMA, and we're going to start by looking at the periodic table, and we're going to note that there's known interferences and interferences we may not know about. Interferences that we can reliably count on are, say, for example, the interference when you're measuring a trace vanadium in a titanium-bearing mineral. You will get interference of titanium K beta on the vanadium. And the same goes for vanadium and chromium, chromium and manganese, manganese and iron. The beta line of each of these elements interferes with the K alpha line of the next element up. And the same is true for the second row transition elements, except this time it's the L beta line interfering with the L alpha line. And the degree of interference depends greatly on all sorts of parameters, such as the element pair in question, and then also the resolution of the spectrometer, and also the crystal and everything else that goes along with that. So some of these interferences we can anticipate, some we might not be able to. Now let's look at the paper that all this is based on. This was published in 1993, and it's basically we derive the interference correction rigorously from first principles, and we end up with an equation that provides the quantitative correction. That paper is available on our website, probesoftware.com, and also on our user forum. So let's start. We're going to run probe EPMA. We're going to make a test run just to demonstrate how we set up these runs. This is for Joel hardware. And we'll make file new. We'll just select a test name and create a new run. And then what we're going to do is we're going to add the elements. First make a new sample, and empty sample. We'll select some elements. We want to measure for molybdenum because that's the element that we're interested in this case. And we also may want to analyze iron. Let's say it's an iron sulfide that we're measuring molybdenum in. And maybe we want to, and then we also need to measure the sulfur. The reason for the sulfur measurement is because we need to analyze for not only the interfered element, but also the interfering element. And if we wanted to, say, do iron copper sulfides, we'd also add copper to that. So let's do that on the LIF crystal. And we move the spectrometer to those positions. You can see here. And when it's done, we close this. We go to elements cations, and we add these elements to our run in whatever order we prefer. We use default settings. This is just a test example. So now we have a sample that contains molybdenum, iron, sulfur, and copper, and of course other elements can be added in addition. We now go to our automate window where we manually acquire standards, and we'll want to acquire a standard for each of these elements. So let's start by adding some standards to the run. We could select pure elements mostly. So let's go ahead and add in iron. Oops, not cobalt. Well, it doesn't hurt. Copper and molybdenum. And for sulfur, we will choose the natural pyrite from UC Berkeley. All right, so now we have our standards, and as you can see here, we've already digitized points for them, so they're ready to go. And we run them just as we normally would, confirm and acquire. And of course, we've already assumed that we've peaked up the elements, each of these elements, run wave scans to check for background interferences, and also adjusted our PHAs. So once we're all done acquiring that data, then we can go ahead and assign the standards. And I will open up a run in which we've already acquired the data to show this. Although you can acquire it in demo mode in Probe EPMA, although the resolution of the virtual microprobe in Probe EPMA is somewhat better than the real world. so you don't get quite as much overlap. So we're going to, actually I said yes to connect to the instrument, but I'm going to change that and say no for reprocessing because the data we acquired was on my Kamika instrument and the software is in Joel mode. So we'll say no to connect to the microprobe, and we'll open up this run a few years ago. When we open the window here, you can see we have our standards, we have an unknown, and the way we start with is we start analyzing each of these standards just to see what we might find. So for example, let's look at the molybdenum standard, which is our primary standard for molybdenum. If we analyze that, we'll notice something right away, and that is that we're getting about 99% molybdenum, which makes sense because it's the primary standard, but we're also getting about 2% sulfur. And that's because molybdenum interferes with sulfur. And of course, sulfur interferes with molybdenum. This is what I call a pathological overlap. So we can go ahead and specify that interference correction. So what we're going to do is select all samples because we generally want to assign the interferences to all our materials, unknown and standards. We click on the element that's interfered with, which is in this case sulfur, and you can see that we've already assigned that standard. We can check that this could be a real interference and not a trace amount by looking at the virtual modeler here, and here's our on-peak position here, and as you can see we're getting lots of molybdenum signal, especially from the L-alpha 1 here. So that is correct. We select the first order line if there's no Roman numeral here. If there are second higher order lines, we can specify the interference order here. So you want to make that Roman numeral match that Roman numeral. And then of course we can use molybdenum because it contains a known amount of molybdenum, which is the interfering element, but no sulfur, which is the interfered element. That is a critical point made clear in this paragraph right here. So we select that, and then of course we've also assigned pyrite as a standard for interference standard for molybdenum because it contains the interfering element sulfur, but none of the molybdenum, the interfered element. And then there's also a minor interference of copper on zinc. And again, as I pointed out, you can model this right quickly here, and here is the interference of the sulfur on molybdenum. And in fact, we can test this by looking at, now it's turned the interference corrections on, and if we go back to our molybdenum and analyze that again, we see that our sulfur is now 0 weight percent, and that's 100% correction. And we also can check by looking at our pyrite material, and we can see that there is no interference of sulfur on molybdenum. In fact, if we turn off the interference correction, here, we can see what that would have been. So here's, again, the same analysis with the interference corrections turned off, and you see we're getting almost 2 weight percent of anomalous molybdenum when there shouldn't be any. But we can turn that back on. And analyze it again. And back to 0. We can also apply this to unknowns, of course. And as you can see, we're essentially 0 molybdenum within 2 standard deviations of 0. Okay. Next, we can also do the same type of analysis for maps. So here's an example of a mapping run for those same elements. And we'll open up this project that we've already imported. And we will here. And there's our mapping run. I've made 2 projects, one without the interference correction, one with the interference correction. That can be turned off very easily, as we saw before. So here's our material, and we can close the off-peak images and just see the on-peak images. And what we will notice here is that it appears, this is our molybdenum map right here, you can see the molybdenum right here, and it looks like we're getting two different levels of molybdenum in these two different sulfides. One's an iron sulfide and one's a copper iron sulfide. Should be pretty obvious which is which. And if we look at the, again, we have the interference correction turned on, and if we look at the map when we export it, we can see that our molybdenum map has no molybdenum in the iron sulfide or the copper iron sulfide. And in fact, the interference is correction now reveals the actual phase that contains the molybdenum, which is a small amount of about 0.28% molybdenum. All right, that's how you correct for quantitative interferences.